Are you an aspiring engineer, a graduate, a student, or anyone interested in the automotive industry? Then today's video is one to watch. Today we'll be talking about a critical topic in the automotive industry: what is an ECU? Let's get to it. Modern day vehicles have so much technology they are basically like computers on wheels. They contain over 100 ECUs or mini computers that allow the vehicle's functionalities to work. So you've probably heard people talking about electronic control units, microcontrollers, engine control units, etc. These are actually all the same thing. It's just that some car manufacturers prefer one name over another. All ECUs together are known as the brain of the vehicle, and they talk to each other and share information over a network of two cables known as CAN high and CAN low. But what actually is an ECU? An ECU is an embedded system that controls one or more electrical systems on the vehicle, essentially like a mini computer, processing all the vehicle's inputs and responding with an action. What do I mean by an embedded system though? An embedded system is a combination of software and hardware designed for a specific function. The software is installed or flashed onto a computer chip. This chip is known as the microcontroller, and it's used to make an ECU by integrating it with a circuit board or PCB with appropriate physical connectors, power circuitry, and mechanical packaging or aluminium casing. The combination of all ECUs on the vehicle make what is usually called the brain of the car. There are many different types of ECUs used for different systems on the vehicle. However, they are generally assigned to a specific system itself. Some examples of different ECUs that can be used are, for example, the transmission ECU, the traction control ECU, the brake ECU, or even the airbag ECU. These different ECUs also have their own assigned sensors that are used for that particular system. For example, the airbag ECU would receive information from its crash sensors and sensors that detect when someone is sitting in a particular seat. Some vehicles may incorporate more than one ECU into a single unit, for example, the powertrain control module. These units can be an advantage by having more modules in one location, but may be a disadvantage by adding longer wires to reach the components or sensors that it operates with. Despite the ECUs having different functions and controlling different systems, internally they all look very similar. So let's take a look inside and see how all these components fit together. So here we have a diagram of the ECU and its various connections. In the centre you can see the microcontroller. The microcontroller forms the base of an ECU. It is where all the inputs are taken in and logically worked upon with the provided software routines or coded script to provide the desired output. These microcontrollers are coupled with other memories such as SRAM, flash RAM or EEPROM memory, where the different software components are stored, be this either the bootloader or the actual firmware and other software parameters required for processing different tasks. On the left hand side we have the inputs, so we can define the inputs to an ECU in two different categories. We have number one, the power supply. These provide the input voltage and current supply for the ECU to power up and function properly. In the second category we have analog and digital inputs. These are one of the most crucial components of an ECU and are the decision making factors in the function of a subsystem. On the right hand side we have the outputs. Based on the input data, we control the output factor. This may be the actuator drivers, the relay, injectors, valves, or H-bridge drivers for servo motors or logic outputs. Next on the diagram we have the communication links. You can see CAN and LIN on the left hand side. It's possible that the location of a sensor and the ECU are at different places on the vehicle, resulting in a requirement for a communication link between the two. Also, at times, a vehicle can contain more than 80 ECUs. Thus, some ECUs outputs are reliant on other ECUs informations, and they are all connected using the CAN, LIN or FlexRay network. Therefore, there is a need for intra as well as inter ECU communication. As a result, communication lines of different communication protocols like the CAN bus, LIN protocol and the FlexRay protocol are integrated with the ECU. Here we can see a real labelled image of the PCB board inside the ECU, detailing some of the real components from the diagram we just talked about. There are some variations of the types of PCB boards, such as ceramic boards, flexible rigid flex, or metal substrate boards. However, the main components inside the ECU are all broadly similar. So in the centre we have the main microprocessor containing the central processing unit, CPU, and the memory. The CAN and flex tray port can also be seen. This is where the communication links we spoke about would be connected, allowing data transfer to the ECU from the various systems and components on the vehicle. We have an ECU reset button which can be used to perform a hard reset on the device, as well as a debug port, which is a diagnostic interface used to troubleshoot issues with the ECU. So here we have a little insider tip about the ECU PCB boards. There is actually a second microprocessor used that oversees the main microprocessor that we've been talking about. It makes sure that if the main microprocessor becomes corrupt, the overseeing processor can step in and turn the ECU off in a safety critical situation. So we now know that we have multiple different systems on a vehicle and an ECU assigned to each of these systems. For example, your brakes, the engine, the chassis, the transmission, the suspension. I could go on for a while. These systems need to work harmoniously together to provide the comfiest and safest driving experience for ourselves. However, if we rewind about 50 years before we had any of these microcontrollers or ECUs, at this point in time there were only a few electronic components in automobiles, and the automotive companies preferred point-to-point wiring systems, where data lines were drawn individually from each component on the vehicle. With the expansion of the automobile industry, more electronic components were incorporated into designs to meet increasingly sophisticated demands. As the number increased, it became challenging to use this point-to-point wiring system due to the complexity, the weight, and the cost of fitting that much cable. Can you imagine the exponential increase in cable weight when a new component was added? Fast forward to present day, each of the main areas on the vehicle has its own dedicated ECU that is programmed specifically to deal with these areas. Now, when I say deal with, I mean they are capable of controlling the sensors and actuators within that area and provide information to the network so the other ECUs connected know what's going on. This capability to communicate with each other was made possible by the introduction of the CAN network in the mid-1980s, a central electrical line connected to all ECUs on the vehicle that allows each of the ECUs to communicate with each other in a broadcasting method. In order to respond to these inputs, the ECU processes information and creates a response through referencing their own internal lookup tables or software. This should all make a little bit more sense as I draw a circuit out on the vehicle framework in the next slide. Here we have a bare chassis with an engine, some wheels, some other components on there. Hopefully this will help us better visualise how the ECUs on the vehicle are connected to this central CAN line. So let's imagine that this CAN line, which runs throughout the whole vehicle, runs directly through this centre, as we can see in yellow. And let's take some ECUs as an example. So we would have the gateway ECU likely somewhere in the middle. We would likely have a engine control unit somewhere over here connected to this CAN line. We might have a body ECU somewhere that's controlling all the body functions on the vehicle. And then we may also have something like a brake ECU. So let's put this somewhere over here. And these are all connected to this central electrical line, which is allowing all of them to communicate with one another. However, these ECUs will also be connected to their own assigned sensors and actuators. For example, with the brake ECU, we would have the pedal sensor somewhere over here where you would be sat, which would be connected to this line. We may also have a brake caliper actuator somewhere over here. These will all be interconnected to feed back information onto this central CAN line. As we looked at the brake example in the previous slide, let's go into a little bit more detail on a modern braking system, the brake-by-wire system, and how this works. So initially the user will press the brake pedal. The force is measured by a sensor. This brake sensor is connected to the brake electronic control unit. It takes this value, checks it in the lookup table, and pulls out the required pressure needed by the brakes. Once it knows the pressure for the rear brakes, it will put this information in a CAN message and send it to the brake actuator to stop the vehicle. But what actually happens when the key is turned on? Let's have a look into the main steps involved in the startup procedure of an ECU. Step 1, power management. This is where the voltages in and out of the ECU are regulated and the power up process is started. Most ECUs need sophisticated power management due to its various different components inside it. Step 2, now the voltages are accurately supplied, the microprocessor begins to start up. The first step the microprocessor does is read some software, more specifically code from its memory, and performs a self-check. Step 3. Providing the self-check is all good, the ECU will read the data from its attached sensors and convert this into useful information and broadcast this as a CAN message onto the network for all the other ECUs to read. Step 4. The ECUs on the network read the information and run it through its internal lookup tables within its software and activate outputs if required. The behaviour in step 4 is consistent throughout the vehicle's operation, so even for example when we press a button on the steering wheel, the related ECU will send a message onto the network for everyone to read and see. But what happens when the vehicle is turned off? If all ECUs were on, when only the ignition is turned on, surely the battery would just go flat. You would think so. However, the ECU has some power saving features that are standard on all ECUs on all vehicles. The ECUs have 3 different modes of operation: normal mode, standby mode and sleep mode. In normal mode, the ECUs are communicating as normal. This has the highest power consumption. The standby mode, this is the transitioning mode when an ECU has been woken from its sleep and is awaiting the system processor to place the transceiver in normal mode. This has a low to medium power consumption when in this state. Lastly, we have the sleep mode. This is where the ECU is off and the only active component is the lower power receiver, so that the ECU can receive a wake up sequence, for example, which will indicate that it needs to turn on. It should be noted that in standby mode and sleep mode, no CAN data from the network will be passed to the ECU's transceiver pin. And just to make it a little bit more complicated, there are a number of special ECUs that are permanently powered, such as keyless entry ECUs or the body ECU. Lastly, to talk about, we have not mentioned the main, most important ECU, which is the gateway ECU. So the communication data transfer between all the automotive protocols and all the ECUs on the vehicle and the cloud has to be managed by a central authority. This is where the central gateway ECU comes in. A central gateway is a hub that interconnects and transfers data across many different networks found in the vehicle in a secure, reliable and dependable manner. It is supposed to provide a physical isolation between different ECUs, controlling various sensors and actuators, and protocol portability translation to route signals between functional domains in a vehicle. For example, information passed between powertrain, chassis, safety and the body control, infotainment, telematics, ADAS systems, and I could go on forever, that share data. In short, the central gateway acts as a router and it enables communication between multi-protocol and connected services. One good example could be newly placed road barriers, for example, placed due to an accident or a construction on a highway. The use of GPS data extracted from the navigation device and vehicle motion information extracted from the Electronic Stability Program ECU or the ESP ECU can be collated with other sensor and actuator data. This collated data is then transmitted to the cloud service, and once a multitude of data from different vehicles passing on that same highway is collected, the vehicle can determine the road barrier's exact location on the highway. This notification can be sent to other vehicles approaching the road barrier, and it will help them avoid the barrier altogether, or it will change the vehicle's path to the destination, or at least make the driver aware of the problems that are ahead. So now we know a bit about how the ECU works. You're probably wondering how the ECUs transmit data onto the network and how they are all interconnected. This is due to a networking protocol called the CAN Controller Area Network, and you really can't miss this if you want to know how ECUs work. So make sure you check out my channel for more automotive engineering videos, and thank you very much for watching. Please don't forget to hit the subscribe button if you liked it, and please check out the rest of my videos if you're interested in the automotive industry. Thank you very much.